keep the time, but let's start. So today is the last lecture from Graciela. So we will finish with this course, and then we will have 2 lectures from Mateus that he is feeling well and he's at the hotel. His lecture will be remotely, and then we will continue with the normal schedule for today. Okay, so let's start, Graciela. So keep the sign to sign later, because we need to start. So you have the coffee break time for sign the presence list. Okay, thank you.
Okay, well, good morning. Let us start with some humph. Okay, so just to remind you what we are doing today. Today we are going to talk about indirect detection and then pass to very light, so indirect detection of WIMPs and things that are related, like that, like dark matter WIMPs, very close in terms of how to detect them. At accelerators, I mentioned very little because you will have 2 lectures next week about this, mostly about FIPS. And I hope at this point you know what FIPS are. What are FIPS? Feebly interacting particles, namely particles that are, okay, so this will be actually, I think, some of the subjects of this. And so we are going to talk about indirect detection of WIMPs, and I wanted to show you when we finish with here. So I'm talking about this, this regime here, WIMPs and particle-like dark matter. And then I will talk, today we are going to talk about axions, axion-like particles, and all this wave-like dark matter. And then this will be it. So let us go to indirect detection. By the way, this comes, so he was, yesterday Pedro was talking about Ice Cube, and he liked very much this picture. And this picture comes from Ice Cube, actually. I stole it from a collaboration. It says Ice Cube. It says, I cannot read this, MBI. I don't know. Niels Bohr Institute. Niels Bohr Institute. This is I stole it. You know, I steal pictures that I like. Whenever I find pictures that this is very nice, boom, taken. That's it. So this comes from Ice Cube. That's why he liked very much this picture from Ice Cube. In any case, I'm not going to talk about all of this. I'm going to talk a short presentation of just very few things that I consider important for indirect detection for WIMPs. And so I will talk about gamma rays and a little bit about cosmic rays. So, so here you have gamma rays. Still, the major detector is the Fermi telescope for gamma rays. It's still going on, it's strong. It has produced a picture in gamma rays of the universe with unprecedented precision. And then you have Cherenkov array. Next generation will be the CTAO in 2 sites, Chile and La Palma. And I will mention AMS. So here you have, what do you look for? An excess of photons coming from where the photons preserve directionality. So you try to see photons from places where you have a lot of dark matter. So dark matter annihilation depends on the density of dark matter square, because you're using dark matter annihilation, so it goes as the density square. Where you have a lot of dark matter? In the center of our galaxy, in galaxies, in dwarf galaxies. Dwarf galaxies are the most dark matter dominated structures in the universe. Some of them have practically very few stars, a lot of dark matter. And then also clusters and so on. when just getting a signal from one of them is not enough, what people do is to superpose them, 15, 20 of those, superposed galaxies, superposed images from clusters and so on, and try to get the signal from them. They call it a stacked. Stacked means that you superpose the images and analyze them together, analyze the stacked ones. Okay, so here it is, indirect limits. So this is one of the subjects I will talk about, indirect limits on dark matter annihilation cross-sections. We have seen the WIMP miracle, and the WIMP miracle has a cross-section, and here I wanted to show you just to remind you, but I'm not sure it will work, because I don't know how to go back here. Where is dark matter 1? This is 2, dark matter 1. So I hope you remember, we went through this. So here you have this cross-section, 310 to the minus 26 centimeter cube per second. And so this is if you have a cross-section of this order, then you get in the early universe you get omega to be what you need to be the dark matter. But we also mentioned that you can have a cross-section that is velocity independent if the annihilation is in S-wave, or depending on the velocity square of the particles annihilating, if the annihilation is in S-waves. There are some particles that, because of the kinematic structure, they cannot have S-wave annihilation. For example, Majorana. Two Majorana fermions can only annihilate in a, so L, the angular momentum L is what dictates what kind of annihilation there is. L equals 0 corresponds to S-wave annihilation. L equals 1 to V square. And this V can be very different. This V, the characteristic velocity, can be very different at the moment of freeze out. At the moment of freeze out is about 0.3 of C over 3. But later on, as I mentioned here, and that's why I wanted to remind you, after the kinetic decoupling, so even after there is chemical decoupling, the interactions that maintain the thermal contact between these particles and the medium continue being in equilibrium because they are scattering cross-sections. So while the exchange of momentum is fast enough, fast with respect to the expansion rate of the universe, then the particles maintain a velocity which is the square root of T over m. At some point, kinetic decoupling happens, and from that moment on, the dark matter particles just redshift. The velocity goes as 1 over the scale factor. So actually changes in this manner. And this can be a very large, a very small factor. So the velocity of WIMPs are extremely cold before getting into galaxies and become heated up because of they acquire the virial velocity. So you see, for example, if you are, the kinetic decoupling, for example, happens at 10 MeVs or 1 GeV. 1 GeV, just to say. No, that's okay. I want it this way, because otherwise I'm going to change back in a second. Just about the thing. I'm going to change back in a second. So this is, I want to compute this factor, for example, when you have a KV. For a temperature of KV, when a structure formation starts forming and so on, KV, without moving that much, this factor here, if the kinetic decoupling happens at the GV, just to say something, and this is a KV, what is this factor? 1 kV over 1 GV, 10 to the minus kV to GV, 6. So this is 10 to the minus 6, right? And here, if I have 1 GV and this particle is 10 GVs or whatever, this will be 10 to the minus 1. If it is 100 GVs, it will be 10 to the minus 2. So you get a velocity which is 10 to the minus 8. This is pretty cold. What is the characteristic velocity of dark matter particles in our galaxy? Huh? It's about the 300 kilometers. So it's 10 to the minus 3. So you pass from 10 to the minus 6 to 10 to the minus 3 when they find in a structure like ours. Huh? Different structures have different, but they are heated up. So now the indirect detection happens in epochs in which this velocity is much smaller than what it is at freeze-out. Therefore, if the scattering cross-section is velocity dependent, it goes as v square. At the moment, at 1 kV, you can have this factor, without counting with this factor. You have something that this v square is 10 to the minus. This factor square would be 10 to the minus 12. And at the moment of freeze-out is about 1/3 the square, which is 10 to the minus 1. So you see that an annihilation cross-section that is velocity dependent could be much smaller later on and much bigger at the moment of freeze-out. Are you with me in this argument? Okay, then I can go back to the, and then I don't do this thing anymore. So now this should go big. Thank you, thank you. Now I don't do this coming back and forth anymore. Okay, so now you can see annihilations during or immediately after the CMB emission that happens at electron volt temperatures or so. This gives you an upper limit. The constraint comes from annihilations, or could be the case, but I'm talking about annihilation, at recombination of later. The Fermi-Lat observations of stacked dwarf galaxies. I told you what the stacked dwarf galaxies are, right? Constraint annihilations at present of dark matter particles bound to galactic halos. V square is 10 to the minus 6, right? The positron spectrum measured by AMS2 this is just a more precise measurement of actual excesses that were also present in previous. This was a satellite, a European satellite, Pamela. And then HEAT was a balloon experiment. HEAT was a balloon experiment in the 1990s. This positron excess was already in the 10 GeV to 100 GeV was already there. Okay. These constraint annihilations at present of the matter particles close to Earth because they are measuring E plus E minus. So what is that you are looking for in terms of this cosmic rays? Positrons are cosmic rays, yes? A balloon experiment. Well, you have to go up in the atmosphere, and so a balloon goes up and measures there instead of a satellite. That was the best you could do. Balloon experiments. There are balloon experiments still, for example, ANITA. ANITA is a balloon experiment that circumnavigates HEAT. I don't remember. Maybe it was also in Antarctica, HEAT. Because they circumnavigate, there are these in summer, of course, in winter you cannot work in Antarctica. In the summer, there are these winds that circumnavigate at the pole. And then your balloon stays for maybe a month, or if you are lucky, depends on winds. And then it falls, of course, and you are lucky if you get any part of your detector back. Okay, so these are balloon experiments. But Pamela was a satellite, and AMS-2, I hope you know, is a module in the space station. I don't know if you knew that. Module in the space station. Actually, this is in this here. Here you have. Here you have. This is one of the docks module in the space station, and they are going to continue actually. There are some if you haven't seen them, there is what experimentalists do. We were commenting today what experimentalists do for their experiments. In this case, AMS last year was about to die out because they have some pumps, and they had 3 pumps, and 2 of them were broken, and they were down to their last pump, and they had to change a pump in space. It's not trivial. They only got 1 person who actually could move. You need an extreme, in any case, this is a parenthesis, but you give an extreme, you need extreme force in your hands to overcome these gloves that are full of, in your spacesuits, that are full of air and so on. They got only 1 of the astronauts actually who had enough strength in his hands to be able to change. And there is a video of that. It's very impressive. It takes out a cover and so on from the experiment to be able to work in. And so what it does with the cover is very impressive. Throws it. And you can imagine how much rubbish there is that the astronauts leave. Of course, that was very short-lived. I'm sure it burned out in a week or 2. But in any case, this is an experiment measuring anomalous cosmic ray. Why do you look for anomalous cosmic ray? In annihilation, any annihilation produces equal numbers of particles and antiparticles. In cosmic rays, you have mostly particles. So you have electrons, but not many positrons. And therefore, an excess in positrons is much more visible, they call it anomalous, than because there are very few. The same thing, antiprotons. Antiprotons is another anomalous cosmic ray. Okay, so now, right, so this is this positron spectrum that was already there from the 1990s. It was measured better. So they all imply that there is a limit. Actually, this sigma v is forbidden at the moment they are measuring. And the moment they are measuring is forbidden. So this implies the limits I'm going to show you in a moment. Imply limits on the WIMP mass of order of 10 GeV. The exact limit depends on the decay annihilation channel that is assumed. If it is BB bar, if it is tau bar, it is so on and so forth. It will be a combination of all of them probably. The exact limit depends on the annihilation mode. And this is the sigma theory. This one is 3 × 10⁻26, which is the upper limit of thermal WIMPs, so that omega is smaller or equal than omega dark matter. It couldn't be larger. This rejects thermal WIMPs that are light enough if annihilation is in S waves. But namely, sigma v is independent it's velocity independent, but it's not constraining for any P wave annihilation in which the annihilation cross-section sigma v is proportional to E squared. This is so because at freeze out, the velocity is a fraction of c, and it is much smaller at recombination and within galaxies. So first of all, dark matter may not annihilate at all. If you have what? I showed you yesterday, asymmetric. right? Asymmetric dark matter, with asymmetric dark matter, you have particles only. You don't have antiparticles. There's no annihilation left. So this is one caveat. Second caveat, you could have things that annihilate, because Majorana fermions could be dark matter and would annihilate. For example, neutralinos or something, they are all Majorana fermions. And they annihilate in P wave. And so they also would be. So here, this is from the CMB limits on dark matter annihilation cross-section. This is from Planck, of course. Dark matter annihilations would heat up the universe close to recombination, would leave an imprint in the CMB. Limits are due to total electromagnetic power injected. So they extend to lower mass, to masses that are much lower than the range of WIMPs, which is about 1 GeV and above. You see here, and it extends also, although here it is not in this plot, it extends lower masses too. And so here it is the this famous 3 10 to the minus 26. And you see actually that for different decay mode, annihilation modes that are assumed, then you have a different range and so on. I will talk a moment, this is the second thing I will present, about the Fermi galactic center excess, which is in sort of minor trouble with this limit. There's more trouble with the next one. So this is the upper limit on annihilating dark matter from the Fermi Space Telescope. This was already in 1916, 6 years ago. And here you can see this is a band due to several uncertainties and also different annihilation modes. And you can see, again, the same thing, the same annihilation cross-section, 3 10 to the minus 26 in this unit, centimeter cube per second. And so the limit here is closer to 100 GeVs. Below 100 GeV would be forbidden. Again, would be forbidden only if this annihilation would be exactly the same as it is in the early universe. But you see here a WIMP with S-wave annihilation that would have this annihilation cross-section in the early universe would have way down V squared 10 to the minus 10 of this annihilation cross-section here. So it is really not bounded by this. You with me? Yeah? Okay, so this is the major point. There are newer versions of these plots. Here I put some. So it's the same thing. Again, these come from stack galaxies. They are a little bit high. You see that the limits become better and better always. This is from AMS and AMS2 is the second generation of AMS. Is the antiproton dark matter measurement, antiproton flux. And this is a limit on the annihilation cross-section. And in yellow, I couldn't write in yellow. In yellow, this comes from a radio, in the limits in the radio spectrum. This comes from electron synchrotron in the Large Magellanic Cloud. That is one of the satellites of our galaxy. And you see that this limit gets to even 1 GeV here. But again, you have to know how to interpret this. So S-wave, this WIMP miracle with S-wave annihilation cross-section is forbidden by this. But it would not be if this would be, so you need, again, I will repeat, you need this annihilation cross-section level in the early universe when the velocity is c/3. But if the cross-section is depending on V square, the cross-section corresponding to this now would be here down. So it is not restricted by this argument. Okay, this is my major point. Because many people say, oh, the WIMP annihilation story is completely forbidden by indirect detection. You have a very clear caveat that this is not the case. It's the case for some, but not for all WIMP miracle candidates. Okay, so this is the point. Now, the excess, yes. The P wave is, again, so S wave would be when the impact parameter is 0. L is 0. The 2 annihilation happens like that. Instead, you could have particles that come, L is 1. So annihilation that starts with L equal 1, L equals 0 is not possible. I don't, I always have, so it's kinematics actually for, because the total state has to be antisymmetric for fermions, right? And you have 2 identical fermions that are annihilating. So seeing the kinematics, actually, you realize that minus 1 is L plus S plus 1. It requires that L be 1. It's, one has to do the kinematics, actually. For example, with Majorana. But there are other candidates that in which, too, you can have this property that S-wave annihilation cannot happen. Galactic center excess, I guess that you have heard about it. It has been with us for now, believe it or not, already I was looking here more than 10 years. This 14 years already, something like that. So in the data from the center of the galaxy, if you subtract everything you know, it remains something. It remains an excess in the center of the galaxy. It's an extended spherical galactic center excess in GeV gamma rays. This is in the data of Fermi. This has been confirmed by many, many groups. So this excess is there. The issue is what is the interpretation of what it is, and that depends on the morphology of the, and so on and so forth, the different details. The major things, it could be either dark matter annihilation, or it could be astrophysical. The major contenders are unresolved millisecond pulsars. And I do not know if you know what millisecond pulsars are. So you know what pulsars are, right? Pulsars. So pulsars are neutron stars. Neutron stars with a jet, due to they have magnetic fields and so on. It's a jet, and they rotate very fast. So they point towards this jet, rotates to Earth, out of Earth. Direction of Earth, in Earth, out Earth, in Earth, out Earth. So you see the pulsation that coming in and out of the jet in the direction of Earth. Then this can be extremely large. Actually, well, just pulsars, not millisecond pulsars. Pulsars that have a period of rotation a little larger, could be seconds or something, are one of the major astrophysical reasons. I mean, people believe that this is the origin of the excess in positrons. The positrons are deviated by magnetic fields, so they can come to Earth, not from very large distance pointing to the sources as photons. They actually can come from the very nearby universe, only a little portion of the galaxy. And antiprotons can come from also deviated by magnetic fields in these energies, can come only from a bigger portion, but the portion of the galaxy. So pulsars are the major believed sources. Geminga, or there are a few pulsars nearby, the sources of the positron excess that I mentioned a moment ago, seen by HEAT, the heat excess, and Pamela, and so on, and now AMS. Now, what this is, millisecond pulsars are pulsars that are eating up a companion galaxy. They only appear because they are eating, for example, a red giant or something, a puffy star, like a red giant and so on. And then the neutron star is eating up this material, not only increasing its size, but also increasing its angular momentum, because this material comes with angular momentum, and so it speeds up the rotation. Imagine a whole neutron star that is a very compact star made of neutrons, is about 10 kilometers, rotating with millisecond period, millisecond pulsars. Why millisecond pulsars? Because they have a spectrum, not for any other reason, actually, because they have a spectrum that could account for with the spectrum that is seen in the excess. Now, there are not so many. So here, if it would be dark matter, you could have this, for example, here there are 2 feet of dark matter. It depends on what annihilation channel you have, BB bar, tau, slightly different annihilation, cross sections, and mass. Now, the big contenders are, as I said, unresolved sources that would be millisecond pulsars because of the spectrum. And there have been, so what is it due? Still 14 years, we are still unresolved in this issue. The jury is still out. So there are some unresolved sources. So how do you see if it is unresolved sources or not? It depends on the characteristics of the image. With unresolved sources, you have this very sketchy type of image. So the difference is in the statistics of the photon counts. And this difference can be quantified. And there is tentative evidence for unresolved point sources population, or a smaller scale structure of a diffuse background. The dark matter would be a diffuse background, and the population of unresolved would have a different statistics. So now, the problem is that people really believe that there were unresolved sources until here there was a paper by Tracy Slater and her student, and the paper is called Dark Matter Strikes Back. And what they did was to inject a dark matter signal, to make a fake signal, dark matter signal, and to consider the background. I don't know if you have heard about the Fermi bubbles. Fermi bubbles are 2 very big structures that were found in gamma rays with the Fermi data. These have been confirmed. These are very energetic. The galactic center excess is at the middle of this. These Fermi bubbles are thought to be the remnants of a period of activity of the central black hole in our galaxy. I don't know if you know that there is a black hole of 3 million solar masses at the center of the galaxy. Fortunately for us, it is not well fed, it is dormant, it is doing nothing except accelerate, making stars very near it move very fast. But in the past, it may have had a jet, as we see in many other galaxies. In active galactic nuclei, which are also black holes in the center of galaxies, you see these jets that inject energy and so on into material. This is considered to be a period in which there was a jet, 2 jets actually, coming out of the black hole and heated up this. Actually, what produces these gamma rays are cosmic rays interacting with something there. In any case, these are remnants. So for the point of dark matter, considering the background that you would have, considering better the background that you would have simply because of the existence of these Fermi bubbles and model sources in the Fermi bubble, they could not distinguish a dark matter signal. And therefore, it is not against having a dark matter signal, actually, to have this statistical evidence which suggests some unresolved sources. But, so this would go in favor of dark matter. But however, there is another argument against being the dark matter, and it is that the galactic excess traces the stellar overdensity of the galactic bulge. There is something that astronomers call the boxy bulge, and this is due to the existence of a bar in our galaxy. I don't know if you know either that we live in a bar galaxy. There is a bar from which there come the spirals. So there is a bar. So this means that the central bulge of the stars and so on is a little deformed and so on. And what they see is actually this deformation, this characteristic shape. But this characteristic shape would be in stars, and this would go in favor of having millisecond pulsars being responsible, which are stars in pairs of stars, right? Star pairs. So no more room for the dark matter. So yes, dark matter, no dark matter, we do not know. And this is all I will say about indirect detection, essentially, these two issues. This is an open issue still. And I think it will be open for a very long time, unless there is a new instrument that can observe much better than Fermi. Okay. Right. In the last half hour of my lectures, I'm going to move to ALPS axions and axion-like particles. Axion-like particles are pseudo-Goldstone bosons. And so here it is. Do you know what is a Goldstone boson? No. All right. So when you have a global symmetry, you know what is a global symmetry of a Lagrangian? Yes, global symmetry. So for example, you have a transformation. The simplest one is a phase. You multiply your fields by a phase, e to the I alpha, right? If alpha is independent of space-time, this is, and it is a symmetry of your Lagrangian. You multiply by that and you get the same Lagrangian back. This is a symmetry. Your Lagrangian density is invariant under this transformation. If alpha is independent of space-time, this is a global symmetry because the phase is the same everywhere in space-time. If alpha is a function of space-time, x mu, then this is a gauge symmetry. So for example, U1 electromagnetism is of this type. It's a gauge symmetry, and you need gauge bosons. A U1 in which you will have alpha, which is a constant, would be a U1 global symmetry. And then when this is spontaneously broken, you get a zero mass boson out. So in general, if you have more complicated symmetries, in this case there is only one generator, which could be the charge. There is only one way of going, of moving, only one thing to do, one operation to do. If you have more complicated structures like SU2 or so on, and these are global and these are spontaneously broken, you get one zero mass boson per generator, per broken generator that doesn't leave invariant the vacuum. Okay, so for example, in nature, you can say that the pions, the three pions, pi plus, pi minus, and pi 0, are the three Goldstone bosons that correspond to the three generators that are broken of an SU2 axial, approximate axial symmetry among quarks, among the quarks up and down. So up and down can be rotated, and And these are in nature. So we have an example of quasi-Goldstone boson. Quasi-Goldstone bosons are there when there is a quasi-symmetry. Namely, the symmetry is not exact. The symmetry would be exact. But this is an approximate symmetry. In the case of the pions, the symmetry that rotates up and down quarks among themselves would be exact if the mass of the up and down would be the same. But the mass of the up and down is slightly different, and therefore it is an approximate symmetry. So here, for a U1, I think I have a picture, actually. At some point, I have a picture, because before, here. So this is the characteristic bottom of a bottle of wine potential that corresponds to having a spontaneously broken, in this case, U1 gauge symmetry. The U1 would be the symmetry in that rotates by a phase. So this is, for example, the real part. This is the imaginary part of the field. And you could make a rotation of the field, a rotation. So you see that here, the minimum would be along the orbit of minima. The existence of an orbit of minima reminds you of the symmetry. But the symmetry is not apparent if you sit in one of these minima anymore. So this is why the symmetry is spontaneously violated. You do not see it any longer in the vacuum, in the minimum in which you live. So if you go here and you try to rotate around this axis, right, the rotation by a phase would correspond to rotate around here. It's not any longer a symmetry, because on one side you have a zero mass, a zero curvature. A curvature in field theory is a mass because it corresponds to a phi square. M square, phi square, you take the second derivative. This is the curvature, is a mass. M square corresponds to the curvature. So the curvature here is zero, and the curvature in this direction is not zero. So if the rotation by a phase is not any longer an apparent symmetry. But the fact that there is an orbit of minima, namely the fact that you can go anywhere here and still have the same physics, is what reminds you that there was a symmetry. Without going very far, for example, if you have a piece of material that can be magnetized, right? Ferromagnet material. At low temperatures, you have the orientation of these magnetic domains in all directions, so there is no one magnetization. If you go to lower temperatures, and this is the same thing that happens here, there is a phase transition in the early universe, very akin to what happens in the appearance of magnetization. You go to lower temperatures, and then these domains that have been oscillating all over actually get frozen, and some direction prevails. So once a full magnetization develops, if you are a very little being living inside the material, you say, well, there is no, the equivalence here would be rotational invariance. There is no rotational invariance anymore. However, the rotational invariance, the symmetry that was before, is still represented by the fact that this magnetization could have happened in any direction. But so in a state in which the ferromagnet has acquired a magnetization, if you live inside the ferromagnet, you don't see anymore that there is symmetry against rotations in 3 dimensions, right? This is the same. Okay. So when the symmetry is not, so here you have your orbit of minima, characteristic orbit of minima. My picture is not going to be as good. Okay, but here, so this would be completely degenerate if the symmetry, so this is the right, and this is the real part, and this is the imaginary part of a field, and this would be a rotation of real and imaginary, okay, changing by a phase. So if the symmetry, the rotation by a phase, is exact, then you get a degenerate orbit of minima, and wherever you go, you will have one component along the orbit of minima. This component is the Goldstone boson, has zero mass, zero curvature. However, if the symmetry is approximate, then what you get is a deformed orbit of minima. So it will be tilted. It will be a little bit higher on one side and a little bit lower in another. So you understand, it be tilted. Well, now the curvature is not exactly zero in the minimum. It's a little bit. So this is a pseudo-Goldstone boson. With this mechanism, you get extremely light bosons. And this is what axions and Alps are. So I'm not going to do justice to what axions are. Let me just say that they solve a very important problem, which is the theta problem of QCD. How it solves it? It solves it because a rotation, a chiral rotation, do you know what is a chiral rotation in a fermion? Chiral rotation. Chiral rotation. So fermions are come in left and right-handed varieties, chiralities they call. So you could, so for example, the electron could be right-handed and could be left-handed. If you rotate by opposite phases, the right-handed and the left-handed, this is a chiral rotation. Chiral rotation, through a mechanism that I'm not going to explain, if you make a chiral rotation in a fermion, this can be reabsorbed. In field theory, it is reabsorbed. It's reabsorbed everywhere, but it appears in the theta term. So if you make a chiral rotation, theta is changed by the phase. So you get, instead of the theta parameter, you get theta plus the phase. So the issue is, if you would have a zero mass, a mass term for a quark, this is a quark, is of this type, Q left bar, Q right plus Q right bar, Q left. Okay? So if there is a mass term, and I make a rotation, you see that here the bar, this bar is a star transconjugated, and there is a gamma matrix, it's the gamma zero. But it involves a complex conjugation. So here, if you rotate this by a phase plus alpha, then you rotate Q left by minus alpha, but then you take the complex conjugate is plus alpha. This changes by e to the 2 alpha. A mass term is not invariant under the chiral rotation. But assume that this would be zero. If there would be a quark that has zero mass. If there is a quark that is zero mass, I can rotate this quark whatever I want in a chiral rotation because there is no mass. And so it doesn't appear anywhere. I could make theta equal to 0. This theta parameter is CP violating, and it appears, it produces an electric dipole moment because the electric dipole moment is CP violating. A magnetic dipole moment is predicted by QED, by electromagnetism, QED, but not and electromagnetism doesn't violate CP. But phenomenologically, this parameter theta has to be extremely small, 10 to the minus 10, although in the Lagrangian could have any value. So this is the problem with the strong CP problem. Now, there are no quarks that have zero mass. But Peccei and Quinn said, hey, There are other ways of generating an extra phase that will end up there. Let me add something to the standard model in such a way that I can make a chiral rotation which will give me an extra phase. This extra phase will go to theta, and I will make it 0. This was the idea. And this is the U1, extra U1 of Peccei-Quinn. It's a chiral symmetry that is imposed through having extra fields in the standard model. What they didn't realize, Peccei and Quinn did not realize, that in so doing, this Peccei-Quinn symmetry is spontaneously violated. It's necessarily spontaneously violated. It's not a symmetry that remains in nature. They didn't realize that they would have a Goldstone boson, a pseudo-Goldstone boson. Steve Weinberg and also Frank Wilczek realized this and published this later. Okay, so let me go to, I have 10 minutes. So here it is. There are several types of Goldstone bosons, pseudo-Goldstone bosons. Axions are one of them. Then there are axion-like particles. So for axions, these couplings are fixed in the theory. For Alps are free. They appear in, there are many different models. They are axion-like particles because they are not forced to couple to the gluons. They are not forced necessarily to couple to photons. This is F mu nu. F mu nu is this is the electromagnetic F mu nu. And they are not forced necessarily to couple to electrons. These are the ways in which you can find them. But there could be other pseudo-Goldstone bosons. Majorons could be pseudo-Goldstone bosons. All of them have the same idea. Now, axions and Alps acquire mass, and through explicit breaking, there is explicit breaking means a true breaking. The symmetry is only approximate. Now, the cosmology of pseudo-Goldstone bosons is really enormously amazing. When the spontaneous symmetry breaking happens in the early universe, so different phases that can occur, different phases, occur in the universe. In the universe, they occur. Patches of the universe that are causally connected, they cannot be larger than CT. They cannot be larger than the horizon. They could be smaller because the coherent length could be smaller. It's something that you compute from your Lagrangian. So there are many different patches. And there are two types of evolutions afterwards. It could be that inflation happens after this spontaneous breaking, and we live in only one domain. So the whole universe has just one phase. But it could also be that inflation doesn't happen after. Inflation has happened before. And so you live in a universe in which there were many different patches. And various different things can happen among these patches. One of the things that can happen is that there are cosmic strings produced. Somebody asked me about the cosmic strings. So cosmic strings happen when there is a correlation. Here you see pi over 2. So this is 0, pi over 2, pi, 3 pi, and so on. So you see that in actual space, there is a correlation in one-to-one correspondence between the phases that you're encountering around the circle and the phases that are in the orbit of minima. That means that at the center, the universe actually, the field doesn't know exactly which phase to take, and it has to pass through this maximum. When it passes through this maximum, it passes through the maximum at the middle, and of course this happens with continuity along a line, and this line that carries this maximum energy is a cosmic string. Cosmic strings have a certain evolution, and cosmic strings afterwards can decay, producing axions, producing Alps. Now, what happens when this, okay, I have 5 minutes. I put my 5 minutes. I gave myself 5 minutes. So what happens when you have now the explicit breaking becomes dynamical? The explicit breaking is very small. So the universe realizes that actually there is a breaking only at much lower temperatures. Instead of having just one minimum, there are models in which you can have something like this, several minima, right? So when the universe, when this breaking, explicit breaking, becomes dynamically important, then around the phase, okay, the phases that are close to the minimum here are driven to the minimum. But what happens with the phase at which there is this little mountain here along the orbit of minima? Where there is a maximum, it cannot go anywhere because there is a maximum. Which way it would go? One way or the other? No way. It's a stable. Okay, this energy is all along some phase, the phase where there is a maximum. And there are walls. There are walls that are connecting strings. So for example, here, there are 3 maxima. And then each string goes to 3 walls, and these 3 walls finish in another string, and so on. There is a string wall system. This string wall system has to annihilate at some point, because otherwise it would get to dominate the energy density of the universe. Just a minute. It will get to dominate the energy density of the universe, and it will be a disaster. And so this is the way in which the way in which it will eventually annihilate is by producing a little difference. These are not entirely degenerate. There is a little difference, and that difference in energy that in the end drives to annihilation. So ALPS can be produced in all these ways. And I have only 1 minute, 3 minutes, according to the 57. Yes, there was a question. Can you leave the question for when I finish? 3 minutes? Okay. 3 minutes and we come back, eh? All right. So here it is. There is a bias. There has to be a bias. This bias drives the annihilation. The annihilation of this string wall system could produce not only ALPS, but also gravitational waves and possible primordial black holes. Now, there is an enormous amount of ways in which people are trying to detect ALPS of all sorts. ALPS can be considered to be a field more than a particle. You know, in quantum mechanics, there is always, what is the particle? A field? Is a wave or is a particle? It depends. You can have both. And so this is the point why it is more a wave-like matter. Because then the occupation number, the overlap, okay, these are very light bosons. The de Broglie wavelength is enormous. So here you have the de Broglie length is 10 to the 4 kilometers when the mass of the particle is 10 to the minus 9 electron volts. When a particle is extended over 10 to the 4 kilometers, do you consider it a particle? Yes, or a field or whatever, but it is. So the occupation number is enormous. In any case, there is detection through in cavities, resonant cavities. You absorb one photon from the magnetic field, and then you emit a photon that, if it is at the resonant frequency of the cavity, you have an enormous Q value. And there are many other ways of trying to detect dielectric haloscope, plasma haloscope, dish antennas, and so forth. I don't have time to go into the more traditional, which is cavities, or the least traditional, because this field A, which is the axion-like particle ALP, modifies the equations of electromagnetism. So through this, you can produce a current which is associated with the density of dark matter because of these modified electromagnetism equations. This is what is done in abracadabra. Abracadabra. You know, again, the name doesn't matter actually, because it's so nice, abracadabra. In any case, I don't know if in Brazil also abracadabra is what magicians say, right? Obviously it's a joke, but in any case, it's a broadband resonant approach to cosmic action detection with an amplifying filtering apparatus. I'm sure they thought a lot about how they could come up with this name, abracadabra. In any case, the next is DM radio. The abracadabra, I saw it. It's a little thing like this. I mean, it is a little thing like this in a bottle like that, which is a dilution refrigerator. It's at MIT. This is what it was. But in any case, DM radio is much bigger and it's done in laboratory. There are, I will mention a few more. Halos, the axion haloscopes of different, but this is DM radio. These are the future of DM radio. There is very nice metamaterials. This is absorption. So you have an absorption of one of these dark matter particles. It could be also a dark photon into a plasmon at the resonance frequency. And these are metamaterials in which the resonance frequency, which is actually the plasma frequency, can be tuned. So you can make a search. This is the alpha. It's being developed, actually, this idea. This is a compilation, you can imagine, of what an amount of work is. You see the masses here is an electron volts, and you go to 10 to the minus 12 electron volts. So this is an enormous amount of range of different type of work. This is all future laboratory. Alpha, DMX, MadMax, an enormous amount. There is another issue. I told you that this theta parameter, this theta parameter enters into the electric dipole moment. So this is a measurement of this coupling. And the coupling, this is extremely nice. I told you that it migrates all the field, but you know, there is a residual little oscillation around the minimum still remaining. This little oscillation around the minimum could produce an oscillating electric dipole moment. And so there are two different ways. Kasparov's cosmic action and spin precession experiments. You would see that the spin precessing in an electric field. This would be actually fantastic. This is being pursued. There is another way of measuring a gradient. If you are in the after inflationary breaking scenario, the production of actions is a mess. As I told you, there are several competing things, emission, and so on. So you expect to have gradients. And these gradients may couple to the spin. This contains the spin of in materials. So you expect to see this in this sense a coupling of the gradients, like the gradient of the field dot the spin. This is what you are trying to measure. So in any case, I have shown you only a few alpha, DM radio, Casper, and if you want to have all of them, go to this website, UCLA Dark Matter 2023. There is another one in 2025 coming. But in any case, every single direct detection, and this is our all direct detection collaboration, is represented here. So you can go there and see all of this. And I think this is my last slide.
Thank you. So we have a question.
I delayed your question, so yeah.
Thank you for the presentation. I don't know if my question makes sense, but My question is about the Higgs mechanism.
The Higgs mechanism?
Because we know that maybe the universe has this potential, right, that allows the Higgs mechanism, but how this phase arrive? Is this something related to the bubble nucleation or something like this? Or?
What you mean is what is the phase transition that generates this? Yeah. We do not know the history of the universe before BBN. This would have happened much earlier. So this is my first proviso. We don't know. If you assume that, even if you assume that you know the history of the universe, because this happens at the characteristic scale, when the temperature is the characteristic scale of the potential. The potential has the characteristic scales of hundreds of GeVs, because this is the mass that you want, 200 GeVs for the, or so on. You're right, the vacuum expectation values of the order of 200 GeVs. So actually the temperature that you will need, if something happens, it will be 200 GeVs. This is much earlier than BBN, and we don't know the history of the universe. But even assuming that history of the universe is, as we know, continuous radiation dominated, and only the particles in the standard model get into the soup, and so on and so forth, even then, we do not know exactly the characteristics of the electroweak phase transition. However, the mass of the Higgs dictates that it is second order. It's a second order phase transition. And this is because the characteristics, you know, I don't know if you know what first order and second order is. First order, there is a jump in the order parameter, which in this case is the Higgs vacuum expectation value. Second order, there is a smooth transition. The characteristics of this depends on the cubic term, not only the cubic term. The cubic term depends on the mass of the Higgs. So in order to have bubble nucleation, bubble formation, you would have had to have a Higgs mass that is below 60 GeV. The Higgs mass is above 60 GeV. So it is second order. So there is a smooth transition. And this is what we know. But this assumes the universe is radiation dominated, blah, 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 right? But even then, so for example, there are things in baryon number generation that you could have bubbles are, at the surface of bubbles, there is a lack of equilibrium, right? That would have helped you. A departure from equilibrium that would have helped you to produce baryon asymmetry in the universe. It doesn't help you because it's second order, there are no bubbles. And the CP violation in standard model is too small. And therefore, you cannot have baryon asymmetry generation, if that's what's your doubt. So it is second order if the universe was radiation dominated. The universe was not, it depends on what happened in the universe at that time and how this happened, how this breaking happened. Does that say?
Thank you. Yeah.
Right.
Okay, we don't have so much time, but if we have one more question, I can take it. Okay, if not, we thanks, and I give the word to Martin.
Okay, so as this is the last talk by Graciela, so I would like to thank in the name of the organizing committee for this fantastic set of lectures. I think we are all extremely happy. So thank you very much for coming.
Thank you for the invitation.